Good morning, everybody. Everybody can hear me loud and clear? Good. So it's a pleasure to be here. And I want to do is talk a little bit about multicore processors and operating systems. And this is an ongoing research project. And so I don't really know what the final word is going to be or the final conclusion. I'm just going to tell you about how we got into this area, what we have learned so far, and where we're going. And in general, I want to talk a little bit and put this in a broader context of doing research in computer systems. And so many of you, I think, are students, and you might be thinking about should I go in computer systems, and how do I find a good problem to work on? And so I'll give you a little bit of my perspective of some of the mistakes I've made, and some of the things that have worked reasonably well. And so the outline of the talk is as follows. I'm going to talk a little bit about why computer systems is very exciting to be in, and this probably applies broadly to computer science, not just computer systems. Then talk a little bit about how to find a research problem, and then we'll move on to the main part of the talk, which is about multicore and what it means for operating systems. And the key question that's sort of behind that part of the talk is a revolution in operating systems necessary, or can we evolve operating systems? In 5 years' time, do we need a completely different design for an operating system or not? So why do I think computer systems is extremely exciting? The main reason, I think, is you can always build anything. You're mostly limited by your imagination. You're not limited by physical laws. If you think about computer science or computer systems in general, they're constructed of two pieces. Think about the Kinect. There's the hardware and the software piece, correct? And one of the nice things about the hardware part is that it's built out of this digital abstraction implemented by a transistor that always has a clear signal, a 0 or a 1, and because it's an active component. This means that you can combine these transistors in large and large circuits and get very complex designs. You think about today's processors, hundreds of millions of transistors, combining actually into a single digital system that works. And if you compare that to analog systems, so if you think about analog systems, if you build larger and larger and larger signals, you accumulate noise as you go. And at some point, the noise is actually, that's like this accumulation of noise in action. The accumulation of noise limits, what actually you can build. And because of the digital abstraction, it doesn't have that property because an active component actually doesn't really have that, and you can build designs that scale and scale and scale. So you get almost unlimited composability. And you think about this, if you look at the number of components, for example, on a chip, correct? There's more components typically than a 747 Boeing has in an internal. And so it is tremendous. And this is not just on the level of abstraction of transistors, correct? This is also on higher level abstractions. Think about the internet. How many components, there's really no limit to how many more computers we can actually connect to it. Again, because there's sort of a strong digital abstraction that's the foundation of it. So that's the hardware side. So the hardware side basically has really no direct physical limits, for composability. In some sense, at the software side, the story's even better, right? It's just software. And there's sort of two main limitations. One, you need some hardware to run it. Typically, is actually not the main constraint. The hardware is powerful enough. And the other part is actually, you have to design your abstractions correctly, and that is actually typically a problem. If you have leaky abstractions, then you start composing this abstraction together. There's some point actually it doesn't work anymore. You can think about leaky abstractions as being sort of the equivalent of noise in analog circuits. Now, luckily, we're actually pretty good, actually building good abstractions, or at least have come up with very successful ones. And actually, it's not that hard for a small team of software designers. For example, take a bunch of components, take a web server, take a database, take a web development environment, and boom, you can actually build a new website, correct? And before you know it, you've built Facebook. And so it's possible to actually be extremely successful. Of course, it's also possible to have extremely failures because you have leaking abstractions. But on the positive side, there is sort of no limit, again, to the composability of software and hardware. So that makes life exciting, but the story is even better, correct? The underlying technology that fuels all this, the hardware and the software, is also actually improving at an exponential rate. In fact, one way to think about it is that the technology improvement is proportional to the technology itself. And this is a unique property, I think, of computer science. So what do we now mean with that? Well, if you build better processors, or faster processors, you can actually run better layout programs. Then, because you're running better layout programs, you can actually build better processors. And so there's a recursion relationship between the technology and the rate of improvement in technology. And very few engineering disciplines that actually have that kind of property. So if you want to write this down mathematically as sort of a joke, you can think about this that, are you taking the derivative of technology over time? It's sort of proportional to technology. And so if you solve that equation, correct, as you well all know, that's an exponential function. So I think if the popular press talks about the rate of technology being an exponential function, it's actually sort of, there's some truth to it. Now, of course, anything that increases at the rate of an exponential function, there has to be some limit. You're going to either run into the limit of speed of light, or some energy limit. But one of the things that is so exciting at this particular point in time, we don't really know exactly what actually is going to be the fundamental limit. Every time that we've run, or the computer science community as a whole has run into some, block or limit, and there have been a way to get around it. Try to exploit another dimension to actually keep continuing, getting these huge improvements. Now, this is all in words, sort of describing that technology improves fast. And one way of seeing that is by looking actually backwards, right? And so here is the computer that we used in my freshman year to do computer programming at the Free University. And it's a fax 1170. It runs at 3 megahertz, correct? Megahertz, not gigahertz. It was a 32-bit machine, $175,000. And 20 students shared it. We were 20 students get into the room. We were allowed to program for an hour, and then we had to leave. And think about this. This thing is slower than your iPhone, right? And less memory, slower clock speed, and actually, your iPhone, you can do a lot more interesting things with. Right? So this is pretty amazing. And that is not. There's only 25 years or something in technology improvement. What also is interesting, actually, I run into this. If you have computers like that, they're time-shared, there are all kinds of rules of behavior. And one of the things that I think is more compelling or most interesting looking backwards is that you're only allowed to use the computer for assignments, for nothing else. No computer games, no email, no Facebook, no other interaction. So what does this mean for systems research? Or if you're in systems research? Well, on one hand, that's great news. On one hand, there's some risks. And the risks are all related to the fact that basically what you can build is limited by your imagination. And if you're limited by what you can build with your imagination, there's some dangers to that. And so I'll give you 2 pitfalls, and both of them that I have fallen into. One, it's actually very easy to do research that is completely irrelevant. You're excited by some technical problem. You think like you can speed up, this particular part of the system by, 10, 25%. You work on it for 4 years. You come up with the solution. Technology, of course, has improved at the same time too. In fact, it has doubled, every year basically. So it's about 8 times as fast, or 16 or 32 times as fast at the end of at 4 years. And so basically, you improved maybe something that what used to be 25 or 10%, you have improved it now by 1%. And most people are not going to be interested anymore. It's going to be hard to get excited about that, right? So, and that's not always true. Sometimes you find a problem and you improve by 25%, and it actually turns out to be really, really important. But it's easily to be wrong. The other thing is, it's very easy to invent solutions that are just too complex. And that has 2 parts to it. If you actually have a complex solution, it's hard for other people to adopt it. And because they don't understand it, there's all kinds of other aspects to it. And so anything that's hard to adopt is probably not going to be adopted. And so there's a real necessity to actually do simple stuff. But there are no natural laws that force you to do things simple, right? Because it's only limited by your own imagination. And it's very easy to dream up complex solutions. There's an even bigger risk is that, of course, it never works. Because it's so complex that you actually never really can get it right. Now, these dangers are compensated by tremendous opportunities, at least in my view. There are continuously new problem areas, opening up because computer technology gets applied in many, many different new areas where it never used to be applied. We've seen a couple examples in Rick's talk, so I won't deliver the point too much. But also interesting is that actually we can resolve old problems. This is like one of these nice things about this field is that you can go back to the problems from the 60s, for example, take the I/O bottleneck, and resolve them using newer technology. For example, solid-state disk can allow new approaches to actually improving the I/O bottleneck. Clearly, any research that actually helps in terms of controlling complexity. Whether it's writing better software, finding bugs in your software, or better abstractions, is going to help with the controlling of the complexity. And I think that's sort of one of the main problems where really things in computer science in general is trying to keep the complexity under control. So any tools that help with that are going to be tremendously valuable. Then there's another class of problems or areas that tend to relate to good research problems, which I call incommensurate scaling problems. These are problems were created because one dimension of technology scales well and another dimension of technology doesn't scale well, and so you get a tension. And often at that point of tension, redesign is necessary. And so one example of that is multi-core processors. Here's a bit of a complex graph, but it's pretty straightforward to read actually in the end. There's years on the x-axis and the rate of improvement on the y-axis, and this is on a log scale. And you can see that the number of transistors on a chip has been sort of doubling every 18 months, following Moore's law. You see here that actually the clock speed also has been doubling, for a long period of time, except then something dramatic happened here in 2001, 2002, where it actually flattened out. And the reason it's flattened out is actually because of the line below that, which actually shows power, the rate of power necessary to actually fuel, these processors. And you see that it reached at some point such a high wattage that actually it was not possible to cool the chip effectively anymore. And so as a result, you can actually not increase the clock speed anymore. And what we see happening in 2001 is that the performance, cycle performance of a processor basically flattens out. So for a single processor, in 2001, 2002, basically things actually have not improved. But at the same time, the number of cores per hash has keep going up. And so what happened? So what did the computer architects decide to do? Well, they said, we're going to give up on give you faster single core, single processor performance. Instead, what you're going to say, we're going to give you more processors, and you go figure out, your software guys, you go figure out actually how to make use of them so that you get better performance. And so now clearly you can't buy a processor that actually doesn't have multiple cores. And so, in fact, most of them have sort of between the 2 and 10 range now. But if you believe that Moore's law is going to continue, and it's likely it is, then at least it will be technically feasible to actually double the number of cores, say, every 18 months. And so we might actually be looking at a large number of cores per processor over a short period of time. At least technically it will be feasible, where of course economically it is exactly the right thing to do, where remains to be seen. So what does that mean for software? Well, that means that our goal is to develop software that allows us to scale with the number of cores. Now what do I mean exactly with scalability? Well, if an application can do 1 unit of work on one processor, what would like to be the case is that we have n processors that can do n units of work. Right? So that's the only way we're going to get better performance. Now, that's the ideal scenario. In practice, of course, scalability is going to be limited by shared resources or shared bottlenecks. For example, if you have a data structure that's shared by multiple cores, you need to protect it probably by locks to maintain some invariant. And that means when that invariant is being executed, every core is going one by one through those sections. And so you're going to not get a perfect speed up. Similarly, there are going to be shared hardware resources. You're going to have one network interface. You're going to receive packets over that network interface. Has to be shared between all cores. So if you think about the runtime of an application, you can sort of split the application in 2 pieces, namely serial work and parallel work, sort of following Amdahl's law. And then basically the runtime of the application is equal to the amount of parallel work divided by n, where n is the number of cores, plus serial time, right? Because that's the part that actually every core executes individually, one by one in order. And so if n goes to a large number, say infinity, then the runtime of the application is going to be dominated by the serial time, correct? And so the key challenge is going to be figuring out techniques that actually reduces S or avoid S. So now so far what I've told you is actually sounds like an incredibly old story. I'm sure Rick is sitting in the corner saying, well, didn't we solve those problems in the 80s or in the early 90s? It's true. In the late 80s and early 90s, there was a lot of research in parallel computing. In fact, this little machine is a shared memory multi-cluster that we actually had at the Free University, which I used in my master thesis. And this is 1987. That's 16 processors, each running at 60 megahertz, which is a little bit slow, but, and it has a shared memory, et cetera, et cetera. So what has changed? Why, so much excitement about it now? And I think the reason is that in 1987, parallel computing didn't address a burning problem. There were, a number of people that really needed to have the maximum number of cycles, but for most people, it actually was not really a particular issue because you could just wait and buy a faster single processor. You just go, wait 6 months, buy the next new processor, and it was twice as fast. And in fact, if you think about it, correct, 16 times 16 is only 256 megahertz, which is slow, compared to any sort of modern processor. So individual processor technology was improving at such a rate that parallel computing was really not a burn problem. It was a niche problem, for some, for example, high-performance computing people. But now, it's completely different, correct? If you want more performance, you want to run more efficient vision algorithms, or and solve them in the same period of time, you cannot go and wait or go to a website and buy a faster single processor. In fact, if you go to an Intel or AMD website, you won't find single processor performance actually listed anymore, and because it's just a constant number. So this has resulted, of course, in the rebirth of parallel computing, because if you want to get higher performance, more CPU cycles per second, the only game you can play is parallel computing. So that's sort of like why parallel computing is sort of an interesting problem, more area to work in again. And so then the question raises, okay, why look at an operating system? This is true for any application, right? And so for any piece of software. And so now I happen to be particularly interested in operating systems, partly because it's a piece of infrastructure used by many applications. And many applications spend actually a lot of time in the operating system these days. If you, for example, take a mail server, we looked at it, measured it a bit, and it's basically roughly 70% of the time actually in the operating system or in the kernel. Reading and writing files, accepting network connections, et cetera, et cetera. So a lot of the sort of the infrastructure that the operating system provides is heavily used by that particular application. But clearly, we like applications like mail servers to scale well from the number of cores. For example, if you're building a big mail server in your data center, it would be nice, actually, if you can use the cores that are going to be available effectively. But if the operating system doesn't scale, correct, and the operating system is a serial bottleneck, then the scalability of the application is going to be limited by the operating system scalability, and so that would be undesirable. So we're sort of interested in the problem of trying to make the operating system as scalable as possible so that applications like mail servers actually can scale well. In addition, the operating system is an instant example of a parallel program. People have spent some bit of time actually trying to parallelize it, and so maybe there are interesting techniques that we can learn or that we also apply to, in general, parallel programming. So what has happened in operating system scalability? A tremendous amount of stuff actually happened in operating scalability, partly due to some of the work that Rick did at Carnegie Mellon on Mach. So 20, 30 years ago, basically most operating systems were uniprocessor. Not all, but many. And had no parallelism at all. But then in the last 20, 25 years, there has been a continuous redesign of operating systems to actually get more parallelism, where it's starting out with fine-grained locks. And I'm going to talk a little bit more specifically about Linux because I have access to the Linux source code. And I can look at it. And it uses a lot of sophisticated techniques. For example, partitions and replicate shared data structures. So for example, in the memory allocator is set up in a way that in principle you always ask memory for your local core, and only when you run out your local core's memory you go ask somebody else. So the memory is basically the memory allocation is divided across the cores so that you don't actually have to use locks, or at least not run into the risk that you have contented locks. In fact, some of the data structures are even lock-free, or read lock-free, so that they can proceed in parallel with write operations. So for example, in Linux, the directory entry cache is a good example of that. And this is all with the goal to actually increase scalability. And so one way to think about it is that the state of the art in operating systems, whether it is Linux or Solaris or Windows, actually embeds a lot of the technologies that was actually invented in the late 80s and the early 90s. Sort of a typical example of people doing sort of fundamental research and actually then gets used when it actually finally turns out to be actually a real problem. But the fact that all these technologies being used has raised in the research community a question about, can we continue down this line? I mean, there's a lot of speculation about future scalability. One problem is that many of these operating systems fundamentally have shared data structures. They're designed as a single address space. And so people worry that these shared data structures in the end are going to really limit the type of scalability that we actually desire. Another problem is that kernels are big. Any operating system kernel runs in the millions of lines of code, and so changing that actually is a challenge. And so maybe operating system designers just cannot keep up with the core count. Like somebody pointed out, made this argument very pointedly by saying, well, if the core count is going to double every 18 months, that means that the length of our serial section needs to be halved every 18 months. So that means like every 18 months, we have to go through all the sort of shared data structures in the kernel and halve their serial sections. That sounds like an undoable job, right? And so we need new operating system designs. And in fact, a lot of people actually have proposed new operating system designs. Not only me, in fact, one of the designs that is listed here, Corey, was actually an operating system that I built with some people at Microsoft Research in Beijing. And we worked on as an answer to sort of exploring, complete new operating system designs. Now, an interesting question, is it really necessary? Is it the case, and there's a debate in the research community, is evolution possible or is revolution necessary? And if you think about this problem, if revolution is necessary, then we better get going very quickly because actually doing a complete operating system from scratch with all these new features is going to take a long period of time. But maybe there's new clever ways that we can think about that allow us actually to scale existing designs in the same way that we have done in the last 20 years. And we don't really know what the answer to this question is, but I'm going to give you a little bit of like my current perspective on it. So in a way, to get a little bit of an answer to this question, we decided to analyze the scalability of Linux. Sort of a prototypical operating system. It's a shared memory operating system. There's a lot of shared data structures. But also people have done quite a bit of more to actually make it run well on shared memory multiprocessors. And so we took a set of applications, system applications, because sort of like thinking about data center scenarios. And we picked applications that are inherently parallel. And so if they don't scale, that's the fault of the operating system, not of the application. And so this was to drive the operating system to see how well actually the things scale today. We ran this on a 48-core machine, which is not exactly the same thing as a 48-core multiprocessor, but it has this particular layout. So there are 8 sockets. Each socket contains 1 chip, and each chip has 6 cores on it. So in the total for 48. Now this is not exactly like a 48-core chip, because this thing has a lot more memory bandwidth than you probably would expect in a future chip. Although with things with 2.5 dimension and stackable memory, that might actually work out fine. The machine actually has cache coherent shared memory, which I'm not going to really explain, but basically says like if one core here, say, does a write to a particular memory location, then another core later, if another core later does a read, it will actually observe the effects of the writes. So we took the 7 applications that are listed here on the x-axis. This is a mail server, Memcache, which is a popular caching application, Apache web server, a database, Gmake, a compilation environment, psearchy, a reverse indexing system, and Metas, which is a MapReduce library for multicore. And here's the improvement. Here's the scalability for these applications if you run them on 48 cores. And you can see some applications do pretty well, like Gmake and Metas actually get pretty good scalability, around the order of 36. Even that is slightly disappointing because most of these 2 applications are predominantly computational intensive. They do spend time in the operating system, but not most of their time. Some applications actually do horrible, like Apache, gets a speed of 1 on 48 cores. So 47 cores are basically doing nothing, right? And so you look at this graph, and this is exactly what we looked originally on. We think that you said, like, well, this looks pretty disappointing. Like revolution is in order. This is, it doesn't look like we're going to fix this with a couple of, bug fixes here and there. And so when we originally run these experiments, that was exactly what we were thinking, and we built a new operating system, which I just mentioned earlier, Corey, with, in collaboration with Micro Research Beijing. But, while we were working on that operating system, we discovered like, a bunch of new techniques, and we said, like, well, hey, but they should apply to any shared memory operating system too. What is really going on with this graph? And so we went back and said, like, okay, let's go understand exactly what's happening with this graph. So I'm going to pick one application, Exim, the mail server, which gets a speed of 8 on 48 cores, and find out what's going on. So here's a graph, that plots, the throughput versus the number of counts on the x-axis. And you see that in the beginning, it sort of follows scalability perfectly. At 4 cores, we get about like 2,000 messages per second done, and at 8 cores, it's almost double, right? So this is perfect scalability. And the line goes up nicely, and then boom, it flattens out, and then there's a dramatic collapse. And so we wanted to know, like, okay, what is the cause of that collapse? Maybe that's the reason why the thing doesn't scale further. Well, we measured the amount of time that the operating system the amount of time that was spent in the operating system. And if you plot that line, it actually is not much until like 36, then it goes up, and then boom, it explodes. So clearly, if you look at this graph, it's the operating system that is actually at fault here, right? It's not the application, which is what you expect, but this confirms it. So now you run a profiler, and you can look at like which function is where is most of the time spent. So we do a differential profile. You run it at 40 cores, you run it at 48 cores, and you find out what the differences is. And you see that at 48 cores, suddenly this one function, lookup mount, 34% of the time is actually spent in that single function, while it actually doesn't show up in the other 40 cores. So clearly, lookup mount is the smoking gun that basically is killing scalability. So let's look at what lookup mount does. This is the complete code for lookup mount. It turns out to be extremely simple. It grabs a lock on the mount table, and the mount table records the mapping from a name to a particular device on which that file is actually located. And to actually find the device on which the file is located, it actually does a hash table lookup on that particular for that particular path name. Now the hash table, hash get function, is actually about tens of lines of code. So this is like nothing. It's like 10, 20 instructions. And so this function that basically executes 10 instructions of legit code is actually cost that, the 34% of all the execution time. So where is that spent? Well, it clearly cannot be the critical section itself, not the hash function, because there's only 10 cycles. And the time actually is spent in the spin locks. So acquiring and releasing that short lock around that critical section is actually the thing that kills performance. It turns out that acquiring a contented lock takes roughly about hundreds of cycles because the cache line has to be transferred from one core to another core. And that transfer across the interconnect is about 100 cycles. So right there, that is like 10 times longer, correct, than the critical section itself. But that's not the real problem. The real problem is that acquisition, because of the way it was implemented in Linux, gets longer and longer as the log gets more contended. As the log gets more contended, and it takes longer to actually acquire that lock, that means actually that the probability of more contention actually goes up. That means that the actual lock acquisition time goes even further up, and this is why you get actually this effect where basically there's a complete collapse. So now what can you do about it? Well, this is a pretty standard problem in parallel computing. So one thing you could do is actually, or partially one solution at least to avoiding the collapse is using scalable locks. But that doesn't really improve your scalability. It just makes sure that when you peak out, you don't drop. Another way is just avoid locks in the common case, right? And it's not that hard actually in this case to rewrite the code to actually avoid locks. What you do, you duplicate or you replicate the hash table on every core. Every core has its own private lock to it, and so then local lookups can go extremely fast. And only when you unmount a file system, you actually have to sort of shoot down all these copies of these mount tables. And that's a much cheaper solution. And because unmount is a very infrequent operation. So we did the sort of same line of reasoning and the same exploration for all these applications that I listed earlier, and came up with solutions for each of individual bottleneck. And most of these solutions are standard parallel computing solutions. They're not actually really that original. In total, we had to modify about 3,000 lines of code in the kernel and about 16 lines of application code. And I'll say a little bit more about that in a second. But with these small modifications, we actually get pretty good speed up. Right now, where XM actually goes up to 28, and makes almost all of them, they're actually around the 36 range. And so basically, with a small number of fixes to a large in the kernel, very crucial, carefully picked out, we can actually get good performance. And this graph suggests, correct, is completely different than the previous graph, and sort of suggests things are maybe not as bad as they actually originally looked like. The key point here, of course, is that most of the improvement here that we're seeing is actually due to actually what the work that the Linux community already had done. The kernel developers already had spent a tremendous amount of time improving the scalability of the operating system, and there were just a couple corners here and there where some work had to be done. And in fact, most of our changes have been redone by the Linux community itself. So in short, looking at that graph, the scalability of Linux is looking pretty good, at least on real hardware. We scale well to 48 cores. But we did some analysis looking at like, okay, what if you wanted to scale to a factor 10 more? What work needs to be necessary? And so, for example, for the mail server application, it turns out we think you have to remove 10 critical sections that you have to work on, but if you remove them, you should get another sort of factor of 10 in scalability. Now, there is a but. And the but is that actually in some cases we actually have to make application changes. And these application changes sometimes are undesirable. So for example, in Pthreads and Metis, we avoided using Pthreads, which is actually a very, common paradigm to write parallel applications. And instead of using Pthreads, you basically created a process for each thread. So we rewrote it to a process-oriented thing so that, and the advantage of that is actually that the memory is not explicitly shared anymore. It makes it much easier thing. Now, that was easy to do for Pthreads, for psearch and Metis, but it's not true for all Pthread applications that you can easily rewrite them to avoid using threads, instead use processes. For example, in the parsec benchmark, there's an application called dedup, which do deduplication, and it uses actually shared memory data structures in a sophisticated way, so it's not actually that easy to split the application back apart and actually make it process-oriented. But it turns out that application, this is run on an 80-core machine, scales well until like 50 cores, and then it flattens out. And the reason it flattens out is because of virtual memory operations. Namely, these threads are doing virtual memory operations, and the operations they're doing actually is allocating and releasing memory, which changes the address space of an application, and that changes to the address space is the thing that actually bottlenecks and limits performance. So we're sort of in a difficult situation. We can't really change the application easily, and so we basically, if we want to get good performance, we need to actually change the operating system. But it turns out, for this particular problem, it's actually not that easy to change the operating system either. So for that, I'd have to dive a little bit more into how an address space works, or is represented. So an address space in almost all operating systems, whether it's Windows or Linux or Solaris, consists of a pretty complex data structure. It has a balanced tree on the left side, which records the region of memory that are actually mapped, so the virtual addresses that are actually mapped. And then there's a set of other data structures on the right side, which is actually correspond on the x86 to the hardware page tables. So those record a mapping from virtual address to physical address. And so the operating system maintains these two data structures to map, be able to implement the illusion that every application has its own machine to itself and translates virtual addresses to physical addresses. The reason that all these operating systems use a form of a balanced tree is because there are many regions. They easily can run in the simple application, you can easily get thousands or 10,000s of regions, and so you want to make the lookup fast, and that's why you want to bind a balanced tree. So what makes it hard to get speed up here? Well, the address space is actually protected by a lock, because if somebody modifies like one core modifies the address space, for example, to allocate memory, and another process in another thread actually goes through and does a lookup, they actually have to make sure that they get the right answers. And so there's a lock on it, and this actually limits is a big problem for soft page fault. So if you think about address spaces, there's sort of three big important operations. Unmapping, so unmapping a piece of memory and removing it from the tree and from the page tables. Mapping it, which basically adds an entry to the tree for a new piece of memory. And then page faults. And soft page faults are taken when the hardware page table don't have an address and mapping from virtual to physical address yet, and then look up in the tree to find the mapping and then install it actually in the hardware page tables. So the hardware page tables are lazily being filled. And so that's typically called a soft page fault. And the Linux operating system, like Solaris and Windows, uses pretty sophisticated ways to actually avoid making page fault to run too slow, but there's still a big problem. And the problem is that when a map or an unmap runs, every other core that actually is taking a soft page fault on a different memory region is going to be blocked by the core that actually holds the lock on the address space data structures. And so when a soft page fault happens at this particular point and the map is actually in progress, then that soft page fault will be delayed. not that it will be delayed on the core that actually, the one core, it will be delayed on every core that actually takes a soft page fault will be delayed. And that is exactly why that dedup application actually doesn't scale. You know, basically there's so many soft page faults that are actually being delayed by map and unmap operations that, you know, that stops the scalability of 50 cores. So that makes you wonder, wouldn't it be cool, correct, if we can take these soft page faults and run them in parallel at the same time that we're doing map and unmap operation? Basically what we'd like to do is remove the read lock from the tree, and then hopefully things can proceed in parallel. The problem with that is you can't really do that because you're going to actually run into race conditions. And the real issue here is that if you do a lookup in parallel with, and another core is actually doing a modification, it may be the case that the tree gets out of balance, and so you need to rotate the tree to actually balance the tree again. And so this can lead to a race condition. So for example, if we have a lookup, you know, going down the tree, reaches node A, and is looking for Z. Well, it looks at the left branch, at the right branch, decides, okay, I have to go right because the subtree, you know, Z is there. But right before it actually traverses the pointer, some other core actually does a rotate to keep the tree balanced because it added some node. So at that point, you know, these nodes actually may get rearranged, and in fact, A's right branch actually may turn out to become Y. So after the rotate, if the other core then proceeds, instead of proceeding down, you know, it will proceed down this right branch, which will end up in the Y subtree, and we'll never find Z. Correct? And so a lookup actually returns the wrong result because the element actually is present, but you're basically right, you know, when core A wanted to go down in the tree, it went down the wrong branch. And so this is why there's a read lock on the tree, you know, to make sure that actually that doesn't happen. So, you know, there turns out the literature, it has a bunch of different, you know, proposals for how to have better trees that actually allow read lock free updates. But we added one, you know, to that rich literature, namely a tree that actually really specialized for this particular case. We call it the Bonsai tree. It allows lookups to be performed in parallel with write or modifications to the tree, but without taking a read lock. And so the scheme is actually inspired by functional data structures. In functional data structures, you never update the data structure in place. Instead, what you do, you sort of conceptually copy the data structure, but you rebuild it by reusing so many of the previous, you know, subtrees as possible. So for example, if we wanted to implement a rotate operation on this tree, we would create the new nodes A prime, B prime, and P prime, hook up and build up the new tree. But this is all done in a way that's not visible yet, you know, to any other core, because only when you update the root pointer, you know, will that new tree actually become visible. So a lookup either runs in the old version of the tree, I mean, before you updated the root pointer, or on the new version of the tree. But in either case, as long as that happens either before or after, it's going to be fine. It's going to return the right result. And what we avoid the problem is that actually, you know, lookup actually goes through the tree and sees an intermediate version of the tree. And the key here is basically the point here that you only update a single pointer at that particular point in time. Now, this scheme is not so good because it requires new copies of the internal nodes from the bottom level to the top. So you have to create log n new nodes. We'd like to avoid that problem, but if you can take the same observation and do a simple optimization and actually avoid, you know, the log n new creation of new nodes by observing that the key point is that only a single pointer must be updated, and then things will stay fine. Well, as soon as if you go up in the tree, as soon as you find a node for which you only have to update a single pointer, you're done. So for example, instead of having going up all the tree, you can actually stop at the node P and update P's right pointer to point to B prime, and you're done. This is nice because now we only create 2 new nodes for every rotation. And so there's a constant overhead, you know, for a rotation operation. The other, and it's a very simple design. So this is a simple design because it, you know, supports reads in parallel with writes, and writes are still serialized. And the writes have to be serialized because for other constraints on the address data structures. Now, there are other solutions that exist, but they're much more complex than this one because we're taking full advantage of the fact that the writes are actually being serialized anyway. So we modified Linux to actually use this, you know, tree, and we only have to do a bunch of other optimizations that are sort of in similar spirit as this tree, but the tree is sort of the key component. And what you see actually, it actually indeed improves performance, you know, from 45 scalability to actually basically almost the full 80 scalability. So the single lock, read lock holding on the tree for soft page fault is the limiting thing that actually scales, that limits the scalability. So what do I take from all the exercises so far? Well, I'm currently much more optimistic about the evolutionary approach. Taking existing operating systems, be smart, and using the sort of most advanced data structures and do a much better job. And I think there's where like the interesting new frontier, at least is for the next couple of years, is that current state of the art use a lot of short critical sections for very fine-grained locks. But I think the next range is basically using data structure that doesn't require locks at all. Now that makes programming very, very difficult, but that's just for the kernel developers. But that allows, as you saw the Bonsai tree is an example of that, that allows actually improved scalability. So I think that one important and interesting direction is starting to use the theoretical results in concurrent data structures and apply them much more aggressively, and also come up with new data structures that allow better scalability. Now, my assumption in all this, of course, in evolution, is that actually shared memory will scale, and that shared memory scalable multiprocessor will exist. And I think that actually is not such a strong assumption, because I'm not requiring that loads and stores to a single memory location will scale. I'm just requiring that loads and stores to different memory locations actually don't interfere with each other. And I think it is people have shown in the past that you can actually build large-scale multiprocessors with shared memory, and I think that those techniques will continue to be help in actually building scalable shared memory multiprocessors. And so you should be able to run shared memory applications on a shared memory multiprocessor. Now, I looked at all these problems, the parallel programming problem, through the lens of an operating system designer. And clearly, there's many other interesting research opportunity. On the programming languages side, and I know Microsoft Research is doing a lot of work in that area, there's a tremendous amount of opportunity to come up with better construct to write parallel programming to make it easy. And if you think about these concurrent data structures, they're a pain in the neck to program with. And we'd like to have solutions so that the programmer doesn't really have to worry about all of the intimate details about like when do you switch a pointer, et cetera, et cetera. Now, clearly in the theory area, there's more room for interesting concurrent data structures, maybe with weaker semantics. On the architecture side, how you build actually scalable shared memory multiprocessors that scale to a large min, et cetera, et cetera. Almost no area sort of computer science that actually cannot be helped by sort of a fundamental breakthrough to actually help make parallel programming actually really come to fruition. So, in summary, what I've told you, I believe that computer systems or computer science in general is exciting as ever. It's still the case that basically what you can build is limited by your own imagination. And so you're not limited by physical laws. And so if you have a creative idea, go for it. I argue there's many exciting areas. The one area that I talked about a bit today is the area of parallel computing. And the reason I'm talking about that is because I feel like it actually solves a real problem now. This is a burning problem. If you want to get more cycles, parallel programming is the only way forward. And there are many tremendous number of research opportunities ranging from, I focus on an operating system, but they range the whole, discipline of computer science. So thank you for your attention, and thanks for listening.